Welcome again. This is some kind of concept, not the problem exactly, because I guess you will all have the solution to this problem. But I'm still discussing it, just feeling the guilt that I'm not discussing enough theoretical concepts. So, this is all about solid angle subtended by base of a cone at its vertex. And I know perhaps many of you know that solid angle has a property of linearity. What I want to tell that solid angle is directly proportional to some kind of length. And what the length is, you will notice here that I have put a cone, I have drawn a cone in green and put its vertex at the center of the sphere. A sphere covering it, and I know that this surface area of a sphere and the base of the cone are subtending same solid angle at the center of the sphere. And then there are lengths. What kind of length? One length is this, from this total diameter, and I know this diameter is this diameter length is this is the diameter of the sphere basically. So this whole diameter can be associated with the surface area to the solid angle subtended by the whole sphere. And there is another length, this one, and we can find this length as well. If the half angle of the cone is theta and the radius of the sphere is r, then this length is simply r cos theta. From here to here, this length is r cos theta, so that this small length can be written as r minus r cos theta. And you will see pretty soon that solid angle subtended by the cone divided by the total solid angle subtended by the sphere can be written as this length, that is r minus r cos theta divided by 2r. And this is the length I was talking about. Kindly pay attention and you can solve many problems related to this concept pretty easily. And you know, this can be written as simply 1 minus cos theta, because by 2, or in fact I would like to write this relation simply as sigma by 2 pi, because 2 gets cancelled out from here, equals 1 minus cos theta, and the solid angle subtended by base of the cone will be 2 pi 1 minus cos theta. You can integrate it to find it, or you can just find it like this, like I did. And it is always true, always correct, always everything. I would like to discuss something else also, because there is a thing called flux. This is basically the flow of electric field lines, and you know this as well. And there is something related to the flux as well. Flow of electric field lines through a closed surface is calculated in a bit different manner. Suppose it's a closed surface, and if lines are coming out of the surface, they are counted as 1, 2, 3, 1, 2, 3, 4, 5 and written simply as +5. If the lines are going to converge at a point in this closed surface, at some point of closed surface, you can count those flow of lines as 1, 2, 3, 4, 5 and call it -5. Give it a -5 because this is beyond any logic. If you will think, this is the plus and minus sign is some kind of notation here who suggests you whether the field is coming, field lines are coming out of a closed surface or going inside the closed surface, nothing else. So if you like to think about flux through a closed surface, and I will show you how to find the flux through an open surface also. But this is a closed surface, arbitrary closed surface. Suppose there is a point charge something here. Then I would like to suggest you draw a unit sphere, a sphere of unit radius. And just think about that. Lines are passing through this. Lines are coming out of this, field lines are coming out of this closed surface. And the number of field lines coming out of this unit sphere is same as coming out of this arbitrary surface areas. And then you know from the definition, simple definition or not simple definition, you can also consider consider those cones we discussed in the idea of solid angle. Here is a patch at this surface S, and here is the patch this, and an element of patch in the direction of position vector, here in the direction of electric field or in the direction of position vector, whatever you like to choose at your will. And they will subtend a cone at the center of this unit sphere where the charge is placed. The charge is Q, suppose that. So flux coming out of the surface, I'm not talking about solid angle subtended by these two surface areas will be the same, because yes, these two surface area are the same, you can see here. And if you like to write, you can write the very basic idea of flux like the flow of electric field, and like this number of field lines coming out of a surface, whether the surface is closed or open. The only thing is the surface area should be perpendicular to the number to the electric field, and so number of field lines per unit normal area to the electric field is simply calculated as termed as the magnitude of electric field. So if this area is ds, the perpendicular area here is ds cos theta. So it is number of field lines coming out, flow out from a closed surface is counted as positive flux. You can write it flux, number of field lines coming out of the surface, equal to, simply you can write here E ds cos theta, and that gives you sort of things like E dot ds. You can put a circle on the integration sign if the surface is closed. If the surface is open, just don't put this circular sign over the integral. And if we can calculate this, the flux passing through the surface, you will simply get, since this is a closed surface, so putting a circle over the integral sign is correct here. And though I would like to use this relationship, and this relationship is simple. This is flux equals suppose that the distance from here to here is r. The point where we are considering this electric field is r from the point charge. Then we can write the magnitude of electric field simply like 1 by 4 pi epsilon naught q by r square. All things are happening in vacuum or air, and just multiply it by ds cos theta. And since you have to make an integration, you can keep the constant terms out of the integration symbol, so that you will have ds cos theta by r square. And this is nothing but the solid angle here. Ds cos theta by r square is the solid angle here. And if you want, you would like to write here the value of integration of solid angle will be 4 pi, so you will get the result q by epsilon naught. And this is the total number of field lines coming out of the surface. There are many mysteries, like if I get 4.234, then what should I write? You will take 4 and like this. So this is flow of electric field or number of field lines coming out of the area. This is positive, counted positive if the field lines are coming out. If field lines are going in, it should be counted negative. That is why sometimes people call it, Gauss called it, Carl Friedrich Gauss, that total flux through a closed surface is simple, a scalar thing. Coming out, they will be due to positive charge inside, so count them plus, and negative charge. So the flux are going in, number of field lines are going in, count them negative. And this is basically algebraic sum of charges, and divided by epsilon naught. This is sometimes called Gauss law. Or you can find flux through the open surface as well. This was a closed surface, so for the open surface you can write here phi equals q by 4 pi epsilon naught, and the surface is open, not closed. You can simply write this thing, that whatever the solid angle subtended by that open surface at the position of point charge located, and you will be calculate the flux received by you, the flow of electric field received by you, and you can put your observer at the surface, so that you can clearly identify the field lines coming to you or moving away from you, and you can put a plus and minus sign accordingly. Or you can write like this: flux through open surface is greater, written like this, for q by epsilon naught multiplied by sigma by 4 pi. And this is a popular thing, and you can find many application of this concept. So I introduced it just as a concept. If you like, you can use it as a problem. Thank you very much for watching.